This will be the talk, Probabilistic Package Builds. Oh no. Okay, hopefully it stays there. So about myself, I'm Daniel Nichols. I'm a graduate student at the University of Maryland, and I had the really cool opportunity to work with the Spack team on a project last year, and I'm going to talk a little bit about that research project today and summarize it for you. So this was, before I get into it, I'm first going to try to motivate what we worked on with a particular problem. So this is some results from a data set within Spack. So what we did, or what I did, was took about 50,000 randomly sampled Spack specs. So that's version, compiler, dependency versions, just sampled a whole bunch of random configurations, concretized them with the Spack Concretizer, which you've already heard about twice today, and then built all the packages. And you see that there's about 34% of those that I did, they concretized, so Spack picked a valid configuration, yet the build still failed, which is not ideal. You want all the selected packages, all the selected configurations to build. You want Spack to either tell you that there's an error with what you asked for, or you want Spack to pick a better configuration. So why does this happen? Mostly because within the package.py files within Spack, there are constraints, and these are human-labeled constraints, which can be error-prone, particularly in these huge sets of packages that are in Spack, and these things change so often, and it's just infeasible to go through and test every version of every package against every version of its dependencies. So you end up with these sort of hand-wavy bounds for version constraints. And that's how you get sort of packages that will concretize but not build, because of these the errors in the constraints. So what we want to do is shrink this gap here. We want all the packages that concretize to build successfully. So an overview of how we approach this, there's a couple different ways you could approach it. You could try to improve those constraints that have the errors within the packages, or you could change the concretizer itself to make use of any extra information you can get to more accurately select versions. So that's what we do here. We make use of historical build information, so previous builds and previous concretizations to make more informed decisions within the concretizer. So the way we first do that is we come up with a representation for the likelihood of a package being built. So this is a way to compact that historical build information into, here we use the representation of the probability of building. So we come up with a machine learning approach to model the likelihood of packages building. And then we use that and integrate that within the concretizer within Spack to pick the most probable build, or the most likely to build configuration. Cool, so I'll jump right into the first part, the build prediction part. I'm gonna briefly go over this because there's actually another talk on this tomorrow afternoon. You should definitely come to that if you're more interested in the ML part of this. But essentially what's happening here is we take a dependency graph for a particular package. Here, for this talk, we'll just look at versions. So this will be the packages at each of their versions within the graph. This will go into a graph neural network. And for this model, here it's predicting whether the package will build successfully or unsuccessfully. Like I said, this will be talked about in more detail tomorrow, but just very briefly, this was trained on about over 40,000 packages, package builds from within Spack, and it, on its testing data set, predicts up to about 91% accuracy. So it's a pretty good model. But for all we care about, it's the inputs and outputs of this model. We're going to consider it a black box and use it for adjusting the concretizer. So what goes in is, say, the dependency graph, and then we're going to modify the output of the model just a little bit. So rather than classification, we're going to look at this regression problem of predicting build probability. So this is really trivial. We just remove the take the softmax output at the end of the model. And so we also narrow this down again more specifically. So this will make sense later why we do this, but we're just going to look at package pairs within the graph. So we're going to get parent-child dependency pairs. So there's a package at a particular version here, PyTorch and Eigen, and we're going to use the model to get the probability of those two packages building successfully. Cool, so that's an overview of the machine learning portion. Now that we have this model, this sort of black box model, and it works, we're going to look at how to integrate that within Spack. So first, I'm going to give just a brief overview of Spack. It's already been talked about twice today, so I won't talk about it too much. The answer set programming part. But essentially, Spack uses this ASP in its solver with Klingo as the implementation of ASP for picking concrete specs, for picking the configuration to build. And so you can sort of see an example of what this looks like here, where different attributes for the spec are put within the logic program, and then you have different rules such as preventing cycles and so on that end up in the program. So there's the big solver for this that takes the abstract specs and computes the concrete specs. And this is what we're going to choose to modify. In particular, we're going to modify the version selection mechanism within the Concretizer to make use of the output to the model. So just a quick look at this. So within Spack, you'll have a bunch of version information. This will come from the metadata within the package.py file, so within the package descriptions. This will list out all the versions. And then you also have all the constraints that come from the package.py files as well. So this is how, within the solver, Spack will specify all the information about what versions are available, what versions don't work with each other. And you'll also see here there are weights within where the versions are declared. So these will be listed from starting at 0 with the most recent version all the way up to n for the oldest version. And what these weights do is Spack uses them for its version selection, particularly to select the most recent version of a package. So barring any constraints or anything else that would prevent a certain version from being selected, Spack will always prefer the most recent version of a package, and that's done by minimizing these weights. So it was mentioned in a previous talk, but the Spack Concretizer has several different optimization levels within it. So when it's picking the stable model or the solution to the solved problem, it will try to minimize these version weights for when it's selecting the version for a package. So if it can, it will pick the lowest one or the most recent version. So now that I've covered that briefly, I'll walk into how we can modify that to take into account the output to the model. So here, what I do is I add in these will-fail facts within the solve call. So this is added to the logic program that Spack uses for concretization. And I do a similar thing where I list off the packages with weights in the orders that I want them. So here we see the parent and child pair at specific versions, so foo at version 1, bar at version 1, and then some integer weight. And so I'll list these in the likelihood, or in the order of the likelihood of build failure. So the lowest one will be the most likely to fail to build for this particular parent-child pair. And like I said here, I'll do this for all the relevant package pairs within this solve call. And then, similar to before, instead of picking the most recent version of a package, I'll pick the least likely to fail, so or minimize the failure likelihood. So what this is essentially doing is picking versions for packages to minimize the failure of or the build failure probability. So this actually works quite well, and it's a pretty, I don't know, easy modification to the existing Spack solver. And I'll show some results for how this works later. But I also, in researching this, discovered there was an extension of Klingo, which is the ASP solver that Spack uses, called Plingo, which is a probabilistic answer set programming solver, and it implements several different variants of probabilistic answer set programming. So I ventured into using that in place of Klingo to do the solves, and using that to incorporate the probabilities from the output of the model. So I'm going to go over a couple of those really quick here, but first a little introduction to Plingo, just so things make sense. There's a lot of extra stuff that Plingo adds, but the core of it, what we'll look at here is just this weight rule. So it allows you to keep the hard rules like in normal Klingo, so you can still have the same logic that a normal Klingo program will have, but you can also add these soft rules where things are weighted by some probability or by some evidence, and then you can solve for the most probable stable models then. So you can say, I observe this fact with some probability p, and I observe another fact with a different probability, and then you can find what the most probable solution is to that solve. So it's a very useful tool, because it also exposes a couple other useful functionalities. So you can find the least probable stable model, you can find the probabilities for all stable models, you can query the probability of particular atoms showing up within the solve solution, which will be useful later. So it's very useful, and like I said, it adds these little facts for specifying probabilities. So this particular one, it's just saying you've observed that Joe is a resident with weight 2, and observed that it's migratory with weight 1. And I'll show some more examples of how to use that as we go. So what I did, it wasn't entirely clear how to encode this within the Concretizer initially, so I implemented a couple different solutions, which I'll talk about here. So this first one adds an ASP constraint using the probabilities. So here, I take those will fail facts like from before, except now I assign them a probability, so their probability of being in the final solution of the solve. And then I constrain against, so I do that for all the pairs. And then I constrain against these. So this is just saying if both of the parent-child are in the model, and this will fail is present in the model, then, or that can't be in the model is what this constraint statement will say. And so this will essentially use the probabilities to remove those packages from the solution as Plingo selecting the solution. The next one I tried was actually modifying Spack's existing conflict mechanism. So you saw this a little bit earlier on one of the slides, but this is what at least conflicts used to look like in Spack 0.20. There's a bunch of conditions, and then there's a conflict fact at the end. Not sure what happened there. But what we do is weight it with a probability like before. So we say these will conflict with some probability. And this is another way of encoding that probability within the Plingo program. And then the final one is to add in error facts with some probability. So this rule is similar again. We encode the probabilities on the will fail atoms, and then we create these build errors based on if those two, the parent-child are in the model, and using this will fail atom to include the probability. And then we add an optimization statement at the end of the program to minimize the total number of build errors in the final solution. So I took all three of these plus the initial one I showed with just Klingo and implemented them to test. So I ran over a set of, this time a smaller set of about 10,000 packages to test what each concretizer, how well they performed, and if they essentially built more packages. So we actually see some promising results here. So default on the far left is this normal Spack concretizer, at least from Spack 0.20. And then native Klingo is the first one I showed, where I just added the integer build likelihood levels, and then optimized or minimized the selection of that weight. And then these are the three Plingo ones that I just talked about in the order. And you can see, thankfully, that one of the Plingo models is actually able to build 13.6% more packages than the standard Spack concretizer, which is great. And they all actually improve over the standard Spack concretizer. So by using this historical build information, we're actually able to select better package configurations and ones that are more likely to build. And then if anyone is wondering, any packages that built in the default also built in all three of these, so we increased the number of packages that were being built, but we also didn't cause any to not build, which is, I guess, sort of an important thing, that we're not messing up any existing builds with this method. So one other little caveat, I'll go over this very quickly, but this method is sort of static to a fixed version of all the packages. So you want to be able to handle as new packages are added and as new versions of each packages are added. And you want to be able to continue computing those probabilities to include within the Plingo program. So I won't go into what each of these implementations are, but we came up with a set of different algorithms for extrapolating those build probabilities based on the outputs from the model. And we're able to come up with a sort of a rule for using extrapolating based on the mean per parent-child pairs. And then we're able to extrapolate for up to a couple new versions, so 3 or 4 within plus or minus 0.03 of the percentage, which is pretty good and means we can use this for extrapolating to new versions. However, it doesn't work for really far into new versions, so past like 5 or 6 new versions of a package, you probably need to recollect build data and retrain the model, or we need to come up with a more clever solution. So another interesting thing that Plingo lets us do, and one of the reasons why I wanted to use Plingo, is we can use it to study the solves themselves and pull out probabilities of individual atoms, probabilities of the stable model, and sort of find out sort of interesting details. And one thing you can do with that is find new constraints for the packages. So like I said at the beginning, with the human label constraints, there might be some that are missing, or there might be some that are wrong. So we can use these Plingo programs to actually study and find what those constraints should be. So if you consider this for a particular solve call, there's a whole bunch of valid solutions to the solve or valid build configurations that Clingo or Plingo might return. And so we want to look at all these and study them, run Plingo over it, and figure out what packages or what constraints might we use based on this build information. However, this solution space is way too large to actually do that. So we can take a sampling of it, so a subset of those solutions, and then assuming we select enough, there should be some of those that have a very low build probability. So the probability of that stable model will be very low, below some threshold. So we'll say below 5% of likelihood to build. And then we can use this to identify likely conflicts. So we can identify parent-child pairs that are within all of these, and then we can also look at their outputs from the model, from the machine learning model with the parent-child, and then we can use those that are most likely to fail. In this particular case, with a good threshold, it almost always works at labeling conflicts. And we can add in those constraints into the package.py files. So very quick test with this. We can see in the middle is the best Plingo one I showed before, and on the left is the default Spack concretizer. But on the far right is the default Spack concretizer, but adding in those new constraints that we computed with the method I just talked about. And we can see that we get about 3% more packages building with those new constraints. So even just pulling out constraints from the Plingo program and not using it as the concretizer, we can still get an improvement in the number of packages being built. So finally, I'll just close with some limitations of this approach and some interesting follow-up work on it. So one of the biggest limitations of this is that it only applies to builds. So any errors that might crop up at runtime due to mismatched versions, like with Python packages or something, would not be caught by this, and it's actually a pretty interesting problem on how to approach that. But we don't currently have any solutions for that. Another one is I talked about how to extrapolate to new versions and apply the same methodology to new versions, but it does not work if you want to add a new package. You'll have to collect more data for that package and then retrain the machine learning model. So there might be easy or clever solutions to fix that, but we currently don't have a way to do that right now. And so looking into the future, there's a couple, I think, interesting directions that I'm either already working on or want to work on. So right now this is just versions, but I think it could be a lot better if it also worked for compilers and the different build variants and build flags. Another interesting thing is, given that this works very well, we would like to maybe deploy it one day, but there's a much more difficult question here. This was a good proof of concept, but it's a lot harder to how do you train those models in such a way that they could work for users on different systems and not cause all sorts of issues? So there's this whole ML ops problem of how to deploy this method. Like I said, Plingo is very useful for being able to query different facts about the solver, trying to see what packages contribute to build failure. I showed one example of it, of identifying new constraints or conflict statements, but I think there's a whole lot of studies you could do with that. So that's another thing I'm hoping to work on. And then finally, another one I really wanted to work on was things other than build success and build failure. So that's probably maybe the most important build outcome you could look at, but you could also look at build time. You could look at the performance of the final binary produced, and so can you select dependencies that give you better final runtime performance. So these are different, I think that this Plingo methodology would work for this, but we need a different initial model to feed into that. But yeah, I think that would be a really interesting and useful tool as well. So yeah, that's the end of it. Thank you for listening. And if we have time for questions, I could take questions.
Yeah, one or two. I'm interested. You use the term error-prone regarding human constraints, and especially when you have something that's checking them. I understand why you might say that, but is there a reason you use the term error? Like, are there particular kind of error cases that you kind of noticed, or are you just kind of saying because humans are finite, they can't do everything? We're naturally going to find more error. I'm interested in what you meant by error-prone that way, and whether there was something behind it at all. And this can be a quick question. I was just interested.
Yeah, so I think I was just saying error-prone in that, just how rapidly packages change and new things are added. It's just infeasible for humans to maintain all those different rules, and that's built, or errors can easily propagate through that process.
I was wondering if you've looked at the model that you have that predicts whether a build may fail or not. Did you look into extracting some kind of patterns from there? For example, if it's implemented in C++ or using Bazel as a build tool, it's more likely to fail, or anything like this?
Like extracting trends from build failure.
Doing lots of predictions and just statistics, basically.
Yeah, so there's a little bit of that. I don't know all of it off the top of my head. A lot of it would be specific to your particular existing software stack and machine that you're on. So, yeah, I don't know that off the top of my head, but we did look at that a little.
Because this may be something that you can use when new packages come in. You can just look what type of package is it, what language is it implemented in, and this can maybe give you some form of prediction, even for totally new stuff you've never seen before.
Mm-hmm. Yeah, I think it could definitely be really useful for that as you accumulate new packages. Yeah.
Anyone else?
Thank you. So earlier on you mentioned inverting the output of the model to find combinations of dependencies that are likely to fail. Mm-hmm. And I was wondering if you've considered implementing some way of package maintainers being able to discover those to aid in their own maintenance.
Yeah, so I guess just search for any particular versions that might fail to begin with. Yeah, so I think that's what this process would be good for searching for packages that are likely to fail. Obviously, this is a bit constrained to the Spack ecosystem, but a similar methodology here could be used for a different ecosystem if you adjusted it slightly to find any particular versions that could be problematic and identify new constraints.
All right, thank you, Daniel. Really appreciate it. Round of applause.